Welcome back, everyone. These are our last set of notes before our winter break. These notes are going to go on page 24 of your interactive notebook. The title for these notes are Valence Electrons and Dot Diagrams. The essential question is, how do valence electrons determine chemical reactions? Let's start by talking about why atoms react with each other. Some atoms on the periodic table are not very stable, and sometimes atoms react with each other to form compounds because the compounds make those atoms more stable. Right? What does it mean when we say the word stable? Here I've got a rubber band. The shape of this rubber band is stable. If I let go of it, it's going to keep its shape. It doesn't need anything special, so it's stable. But if I stretch the rubber band, it becomes unstable. I have to hold it like this to make it keep its shape. If I let go, then it snaps back and it no longer holds that shape. This shape is unstable. Okay, so atoms want to be stable. Everything in the universe wants to be in its most stable, lowest energy form. And atoms are no exception. So how does this work? What actually makes an atom stable? It has to do with the valence electrons. Everything talking about chemical reactions and atom stability has to do with valence electrons. If the outer energy level is full, okay, remember the outer energy level, your valence shell, your valence electrons. If it's full, then the atoms are already going to be stable and it won't want to react with other atoms. A full outer energy level contains 8 electrons. Okay, so atoms that have 8 electrons in their valence shell, in their outer energy level, they're stable. There is one exception to this. Helium can have a full outer shell with only 2 electrons. Why do you think that is? I'm not going to tell you. Some of you guys might be able to figure that out on your own, and we'll talk about it in our synchronous class. So let's take a look at neon. Neon has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outer energy level. So neon's already stable, and it's not really going to react with any other atoms on the periodic table. In fact, neon belongs to the classification or the group called the noble gases. And the noble gases are generally thought to be inert gases. That means they don't really react with anything because they have 8 electrons in that valence shell. But carbon, on the other hand, carbon has 1, 2, 3, 4 electrons in its outer energy level. Because it's not full, carbon is unstable, and so it will undergo chemical reactions with other elements. So atoms can react with each other to share, lose, or gain electrons in that outer energy level in order to become full. What's that look like? Well, here I have 2 oxygen atoms, and they're sharing some electrons in that outer energy level. And since they're sharing, that allows them to go up to 8, right? So 1, 2, 3, 4, 5, 6, 7, 8 because of the sharing, right? That makes them stable. And that's why some elements like oxygen always exist as diatomic elements, because this is their stable form. Another thing that some atoms can do is they can lose, like sodium is doing, or they can gain, like chlorine is doing here, right? So when sodium loses an electron, let's see if I can pause this. No, I can't. then you can see it reveals that other energy level here becomes the outer energy level, and now it's full. Chlorine only needed one more to become full, and now it is. So these are just different ways that atoms can become more stable by filling their outer energy level, and that is the key. All right, so not all atoms can react with each other though, and we're going to be learning more about that after winter break. All right, so how do I know if two atoms will react? Well, the number of valence electrons decide if or how an atom will react with another atom. So here's a Bohr model that shows us an element that has one valence electron. All right, so remember, this was our definition from last week. A valence electron is the electron or electrons in the outer energy level of an atom. So this is our valence electron for this atom. Bohr models are great for showing us the structure of atoms, but they give us more information than we need when we're learning about chemical reactions. When we're learning about chemical reactions, we only need to know how many valence electrons. We don't need to know how many neutrons and protons and how many other electrons are inside the electron cloud. So we simplify it to include only the element symbol and only the valence electrons. So this is our Bohr model that we have been using, and we simplify it to show just the element symbol and just the electrons that are in the outside energy level around the symbol. And I'm going to show you how to do these, or how to make your own. All right, so normally when we have an element in a Bohr model like oxygen here, right, we have our electrons, we have our 8 protons and 8 neutrons in the nucleus, but it's these electrons outside that do the reacting in a chemical reaction. So it's these 1, 2, 3, 4, 5, 6 electrons that are important. To draw the dot diagram for oxygen, we're going to write the element symbol, and then we're going to put the valence electrons, those 6 valence electrons, from the outer energy level around the element symbol like this. We're going to place the dots on the 4 sides, pretending it's a square, on the 4 sides of the oxygen. We're going to go around 1 time before we start adding pairs. So now I have 1, 2, 3, 4. I need 2 more. And that is all there is to it. That is my electron dot diagram for oxygen. It gets even easier than this though. You can make the dot diagram for any A group element quickly and easily just by looking at the periodic table and the group number above those columns. Right? Remember that the group number will tell you how many valence electrons each element in that column has. That's going to be your number of dots. So let's take a look at some examples. All right, but first here's a copy of our periodic table. Remember, these are the A group elements. We don't look at the ones in the middle or the ones down at the bottom. They're part of the middle. Those are the B group elements, okay? So in the A group elements, we have column 1, that's group 1, group 2A, group 3A, 4A, 5A, 6A, 7A, and 8A. And that corresponds to how many valence electrons the elements will have. So if I pick element number 19, potassium, potassium has 1 valence electron. If I go pick another random element, let me pick phosphorus. It's in group 5A. Guess how many valence electrons it has? 5. Okay, so the column number, the group number, will tell you how many valence electrons. So let's take a look at a few examples. So here we have a periodic table that has the different columns labeled 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A, right? That makes sense because we can only have up to 8 electrons in the outermost energy level. That's when it's full, right? And these are the B group elements that don't really follow these rules, so we can't really make these dot diagrams with the rules that I'm showing you, okay? So for aluminum, we have our element in the 3A column, right? The 3A group. We're going to write down the element symbol, which is Al. And then since it's in 3A, that means it has 3 valence electrons. That means we need 3 dots around the symbol. So we'll go back up here and we'll write our element symbol Al. And then we'll make some dots. 1, 2, 3. Now notice I'm going around first. I'm not pairing them up right away. Right? If you make your dots like this, let's see here, that would be incorrect. Okay, so this is not the way that you do this. You have to go around with your dots. All right, so we're going to take a look at a couple more of these. All right, so next let's do sodium. Let's see here. So sodium has the element symbol Na, right? And actually stands for, I believe it's Nasturnum. That was one of its old names, right? And so we have the element symbol Na. And then we're interested in knowing the group number, right? So the group number tells us the number of valence electrons. So how many dots to use. And there's only 1 dot to add because it's group 1A. All right, so that's sodium. Every element in that first column would have the same dot diagram. It would have a different element symbol, but they would all have 1 dot. All right, lastly, we'll do iodine. So we want the element symbol for iodine, and then we want to know the group number. Okay, so here is the element. Oh, I need to go one more slide. Here is the element iodine down here. It is in group 7A. So how many dots do you think I'm going to have to put around my iodine symbol? If you said 7, you're correct, right? But make sure you go around 1 time first, 1, 2, 3, 4 times, and then go around again. Okay, now I have a total of 7 dots around my iodine, and all of the elements are going to have 7 dots if they're in the 7A group. All right, so that's how these work. You will do some of this for practice. in our synchronous meeting on Thursday and Friday. It's not too difficult once you get the hang of it. All right, I'll see you later.